From the Hebrew University of Jerusalem, who would talk about the Yanai waves and classification of westward propagating waves on the rotating spherical Earth.
Thank you, Alison. Thank you, guys. There's going to be no GCM and no data, so you can all relax and just open up and feel free. The idea behind my talk is to it's part of a project in which we're trying to do GFD on a sphere, which was done in the last 50 years, mostly in Cartesian coordinates. And the Yanai waves are what George called earlier 4 talks ago, the mixed, what do you call it? Mixed Rossby gravity, MRG. Right. So it's the same thing. So here's what I'm going to do in the next 15 minutes. I'm going to repeat a little bit, 2 minutes on Matsuno's original work on the mixed mode, and then compare it with what's happening on a sphere and how much the spherical problem is so much more complex than the Cartesian one. And then I'm going to show you a little bit of what we can do analytically, and then tie it all together, connecting solutions in various asymptotic regimes to come up with a clear scenario. And if you want to fall asleep in the next 15 minutes, I can tell you that there are Yanai waves or mixed Rossby gravity wave on a sphere. So this is the take-home message. It's not so obvious because Kelvin waves, for example, are not a separate mode on a sphere. Okay, so let's see how we can compare the Cartesian coordinate version of the shallow water equations on the equatorial beta plane or on any other Cartesian coordinates and on a sphere. Here you can see the equations, shallow water equations on a sphere and on the beta plane, and in both cases we can easily decompose it into a zonally propagating wave, which has the form of wave number k and phase speed c in both cases. Since in the zonal momentum equation there are no y or meridional derivatives, we can eliminate u from these systems, and by slightly redefining the variables, get a system 2 exact a system of 2 equations, 2 first-order equations, both on the beta plane and on a sphere. And if you are a sharp eye, you can see how you can translate from the equatorial beta plane or the mid-latitude beta plane to the sphere by just calling f a different name, so replacing c by c cosine phi, and so on. So we know how to go back and forth, if you will, from the Cartesian coordinate counterpart of the momentum or the shallow water equation to the spherical one. Now, we can solve both systems, i.e. on the beta plane and on a sphere, easily numerically. So there is no problem in doing so. I'll actually do it and show you numerical results. But in order to understand what we're seeing and get some analytical insight into them, it is advantageous, and this is what has been done in all cases, to eliminate one of the 2 variables, v or eta in both cases, and get a second-order equation for the other. So if we eliminate eta, we get a second-order equation for v, and vice versa. So if you go back to the equatorial beta plane in Matsuno's seminal theory, what happens if you do it, in other words, if you eliminate eta, then you get a very simple, well-known equation from quantum mechanics of harmonic oscillator in which you have an energy made up of various constants of the model, and you have a potential which is proportional to f squared. F is beta y. Under a certain scaling, this is what you get. And since it's a well-known equation that was studied in quantum mechanics, we can now go and we know what the energy values are. It's 2n plus 1, and each energy gives us 3 omegas via this cubic relationship between the frequencies and the energy level of the Schrödinger equation. And the resulting picture is a very similar one to what George showed us earlier in this session. And note that for n equals 0, if you plug in omega equals minus k, you get an explosion in the zonal momentum equation, which we eliminated. So one of the roots of the cubic equation in the case of n equals 0 violates the shallow water equations. It yields a singular zonal velocity, okay, because of this term in the denominator. The only way to resolve it is to put in v equals 0, which brings about the Kelvin wave, but that's a different issue. So this is the resulting picture. On the beta plane, we have three waves: eastward inertial gravity, westward inertial gravity, and what we call Rossby wave, equatorial Rossby waves for all n greater than 1. For the case n equals 0, we have no westward propagating inertial gravity wave, which means that you only have one westward propagating inertial gravity wave. And as Matsuno called it, it's called the mixed mode that becomes inertial gravity mode for small k and the Rossby wave for large k, and somehow arbitrarily you can put the transition at k squared equal 2 for various reasons which Matsuno already dealt with. So the question is, on a sphere, U is regular everywhere, so there should be a second westward propagating inertial gravity wave. So is there a mixed mode or a Yanai wave on a sphere? And forget about the Kelvin. Kelvin is actually part of the inertial gravity waves. We're not going to talk about it. So if you do the same thing on a sphere, now let's dash through. Here is the second, the two equation, okay, the second order set. You can do the same trick. On a sphere, you also get a non-dimensional parameter called lamp number. Here it's designated as epsilon, which is the inverse of the square of the speed of gravity waves on a sphere. And the equations are horrific. The reason I don't want you to see them because it's a nightmare. So I want you to sleep well tonight, and we're just going to move ahead and show you what we can do with these horrific two equations. But notice that we can both eliminate V and eta and get two horrific-looking equations. The details are unimportant. They are very complex. But there are two ways of getting a single second-order equation from this system too. Okay, so here is what I'm just summarizing what we can do with it. We can do one thing is get when omega squared is very large, then this term vanishes, and then we have a singularity. This term, I'm sorry, for large omega squared it doesn't vanish. Therefore, we can get an approximate Schrödinger equation for a function which is related to eta. If we have a low frequency wave, then we can get this term vanishes in the low frequency, at least in some case, for some phi's, and we can get the eigenfunction that depends on V, and one of them will be for Rossby waves, one of them will going to be for inertial gravity waves. We can also get an exact solution when we put in k equals to 0, and we can sort of portray the entire picture by just connecting solutions in different regimes. And remember the dispersion curves should be smooth and continuous, and the eigenfunction shouldn't depend very much on the values of k. So here is a cartoon of what we have. We have one region in which we have no approximation, region 1, no approximate Schrödinger equation. Region 2 is where we have the low frequency, then this is the Rossby wave in which we have a Schrödinger equation that results from V or elimination of eta. In the large frequency, region 3, we have a Schrödinger equation related to eta, to the other variable. And in V, in 4, I'm sorry, we have both equations that can provide an approximation, which means none of them can be a solution. The eigenfunctions cannot be a combination of an eigenfunction and its derivative, and therefore region 4 will have no solutions. The additional piece of information is that when k equals 0, we have a solution. That's the third region with a solution. And also, this is a very long and elaborate analysis, but along the omega equals minus k, the anti-Kelvin line, we have a single transition. So there's one value of k, here it is given here, in which we have a solution. So we have a solution in region 2, in 3, along the k equals 0, and one solution along the omega equals minus k. The only way to connect it is in the following way. I'm showing here the first, the third, first, second, fourth, and sixth, I think, regions for epsilon of 16. The region wide 16 because it has a nice looking fourth root. And you can see here what happens in region 1, 2, 3, and 4. And you see how the solutions cross the omega equal minus k line very smoothly, but only one of them. And since only one can cross it, then the n equals 0, or the first mode in region 2, must connect with the first mode along the omega equals k, which leaves no room for the other mode. The other mode cannot stay in one region and cannot cross the omega equals minus k, so therefore it disappears. And the same thing happens for epsilon of 10 to the fourth, the lambda number of 10 to the fourth, exactly the same thing. The solutions are smooth. Here is a zoom in. You can see how it goes from region 1 into the k equals 0, crossing the omega equals minus k line, even though, remember, I'm using the Schrödinger equation formulation and not invoking u. If you look at the eigenfunction along this special n equals 0 mode, you see that along the k equals 0, it has this structure. Here they will have no solution, but in region 2, the only thing you see that varies with k is the width of this Gaussian, as is expected for this low value of epsilon. Ellison, are you sleeping? You should tell me now to hurry up. No, not yet. Okay. And the same thing happened when epsilon is 10 to the fourth. Again, along the k equals 0, we have analytic solution. Along k equals 1, you only have a numerical solution. But as you see, with this large value of epsilon, lambda number, k makes much less of a difference in the structure of the V eigenfunction. Okay. I would like to examine why isn't there a second mode? And for that, I'll take the approximate solutions, which are not exact, because remember, the analytic approximate solution is valid as you are away from the omega equals minus k curve and not at the omega minus k curve. So if you look now at the approximate solution, in the line along which it violates its asymptotic limit, in other words, along the omega equals k, then you realize that the approximate solution yields a complex root. In other words, you have solutions here which you cannot trust, but here you only have one of them, which means that you have a complex root, i.e. instability. Something is goofy with the approximate solution, and it doesn't have to be to yield an approximate solution because it violates the very essence of its origin, namely omega squared, much less than k squared. I hope I convinced you that there is a mixed mode, and I hope I convinced you that on a sphere it has nothing to do with the vanishing of the zonal velocity. And just to sum up before Ellison yells at me, the eigenmodes in one of the regions, the low frequency region, have to connect smoothly with those along k equals 0, the zonally symmetric, since both are derived from V. Only one of them can cross the omega equals minus k. Now you're doing your job. Only one of them can cross the omega equals minus k. The second cannot exist because it can neither stay in one region nor cross the omega equal k, and therefore it disappears. The approximate solutions give you a complex root there, and therefore the Ni wave, also known as the mixed Rossby gravity or gravity Rossby mode, exists on a sphere, although U is regular there. And thank you very much.
Are there any questions? We're actually like 2 minutes ahead of schedule, so yes.
Very much so. Here you see the equatorial trapping. It's right there at the equator. And the larger the value of epsilon is, the more the trapping is. Actually, epsilon and k squared add up in a very peculiar way, which is known. It's not new, but they sort of complement each other.
Any other questions? I have a quick question, actually.
Oh.
If you plot the dispersion relations that you get from the sphere against observations, do you have a better fit to observations than you do from the equatorial beta plane?
It depends on the value. It depends on the value of epsilon.
That you choose.
when George does it, it fits very well.